Welcome to the 7th installment of Unit 3, where we start talking about relative velocity. So this is the last part of Unit 3. This will be the first time we talk about things that are relative, but the next time will probably be in May when we talk about special relativity, which is what Einstein figured out. Right now, though, we're not dealing with that. We're just talking about relative velocity and what really does that mean, because velocity is relative. If you've ever heard that time is relative, that's an important idea. So, what do we mean by relativity? Things are just relative to something else. Everything that we talk about, even if we don't say it, is a speed or a time or an acceleration relative to something else. So, they always are relative to. That's what it means to be in relativity, which is just like this picture, and M.C. Escher is, quite famous for these types of things where, depending on how you look at it, what you see is very, very different. You might have also seen the young and old lady photo. Same type of thing where things are relative to what you see. But to know what we're talking about, we need to talk about what a frame of reference is, so that we can handle velocities being relative to something else. So a frame of reference is whatever you are considering to be at rest when describing the motion of another object compared to it. So what does that mean? So imagine you're sitting in your chair watching this video or in class, and you would consider yourself to be at rest. You're not moving. And that's a reference to you're not moving compared to the surface of the earth or the floor of the classroom, which is the same as the surface of the earth. But really, the surface of the earth is spinning. So in a different reference frame, if we think about the reference frame as the center of the earth, we would actually be moving at 300 meters per second, even though we don't feel it, just by changing our reference frame. And if we made the reference frame to be at rest the center of the sun, then we're actually going at 30,000 meters per second, because that's how fast we're moving around the sun in the solar system. So it's just always, how does velocity change depending on what we're comparing it to? Everything we've done this year has been a velocity compared to the surface of the earth, because that's just what we work with. Now we're going to start to get things a little bit differently. So let's look at a simple example, which we can figure out without any mathematics, and then we'll apply the mathematics to it after. You're on a bus. The bus is traveling east, down the road at 8 meters per second. You have just gotten on the bus, and you're walking towards the back of it at 2 meters per second relative to the bus. So that means if the bus wasn't moving, or whether it's moving or not, on the bus you are moving 2 meters per second towards the back of it. Hopefully it's not too much a surprise then that if we were going 8 meters per second east, we can consider that 2 meters per second we're going on the bus a west direction, which added together would give us 6 meters per second east. Well, now that you've got to the back of the bus, you've sat down for a little bit, the bus is still going 8 meters per second east, but you decided to walk to the front now at the same speed. So now we're going in the same direction. So now we're going 2 meters per second, and we could think of that as going east. So if we're going 2 meters per second and 6 meters per second east, this situation we end up going not 8, but 10 meters per second east. Hopefully that makes sense in terms of thinking about it. But let's put some mathematics to it, and how we're going to do that is looking at the reference frames and using a system that involves double subscripts. So, let's start with what we know. We know the speed of the bus is 8 meters per second. So if we look at problem A, this would be the speed, our vectored velocity of the bus compared to the ground, because that's what it would be in reference to at the surface of the Earth, is 8 meters per second east. Then we're told that the speed of the person compared to the bus is 2 meters per second, and that would be west because it's going in backwards. And what we're looking for is the speed of the person compared to the bus. So you'll see there that we've got 3 different subscripts that we're using. We're using a bus, a person, and the ground, which this last one should be the person to the ground, not to person to the ground, not person to the bus. So we've got person to the ground, bus to the ground, and person to the bus. A relative velocity question will always have this same pattern when we want to solve it, such that the velocity of the person to the ground is the velocity of the person to the bus plus the velocity of the bus to the ground. The pattern is we see this appear first, the ground subscript appears absolute last, and then the in-between subscript is our third one in the situation. So that's the pattern that we always need to have. In this case, we can just plug our numbers in right away, and we would get it's person to the bus, so 2 meters per second west, plus bus to the ground, which is 8 meters per second east, which will give us, as we expected, 6 meters per second east. Now, if we set up the second one, where now we have v bus to the ground is the same, and v of the person to the bus is slightly different, where we get east because we're going forward, and looking for the same thing, person to the ground, our equation ends up being the same because always following the same order of subscript, so that PG is our P is our first, and G is our last, and then our other one is in between. And we get 2 meters per second east plus 8 meters per second east equals 10 meters per second east. When things are in a straight line, it's often very easy to solve. But what we actually want to be able to do is do things in 2 dimensions. So, just like we saw with projectiles, when we're doing anything with relative velocities in 2 dimensions, anything horizontal does not affect anything in the vertical, and the other way around. Those 2 things are independent, and time is the same for both. So those same 2 big ideas work with relative velocity as they did with projectiles. Treat x and y separately, and time is the same in both. And then we'll do a lot of vector work as well. So we've got a motorboat heads east across a river at 8 meters per second. The river flows north at 5 meters per second. What is the resultant velocity? So the velocity is going to have both an angle and a magnitude. What we need to figure out first is what we actually do know. So let's draw a little picture. We've got the shoreline on one side. We've got a boat, a little motor on the back there, and we're standing on the boat, and we're driving it, and we're going east across the river. The other side of the river is over here, and the river current is going this way, north. Okay. Let's translate that into subscripts. So we've got the velocity of the boat. Now what is it going to be compared to? That speed would be to the water, because that's the speed the boat would go at if in still water. Not compared to the shore, but compared to the water. That's just the direction that you're pointing on the water, so that is relative to the water, and that's 8.0 meters per second east. Velocity what's the other thing we know? We know the river flowing, so that would be the water, and water flowing is being compared to the shoreline, so water compared to the shore, which is equal to 5.0 meters per second north. And what are we looking for? We're looking for the resultant velocity. So imagine you were somewhere else watching this person drive the boat. What is the velocity you would see them be traveling at? U would be a reference point that is the same as the shore. So we are looking for the speed of the boat relative to the shore. You can always make sure that you've got your subscripts right, because if you should only ever have 3 different letters, and there should be shouldn't be repeated anywhere. So you've got BW, WS, and BS. Now we set up our equation that would lead us to solving it. Velocity of the boat to the shore, follow our pattern. B is first, and then we know over here S will be super last, and a W will go in between. Make sure we have BW and WS, which we do. We can plug everything in. 8 meters per second east plus 5.0 meters per second north. Problem here is we don't have an ability to just add those directly. We have to draw the vectors and add the components. So we've got VBW, VWS, and VBS there. And we'd have to get our angle. I'm going to leave that for you guys to do. We'll take it up in class and watch there's going to be a second video that has a quick second example with just some more pointers on how to do this.